Good morning. So today we continue with ray tracing. In the last class we looked at tracing some specific rays, namely the chief ray and the axial ray, and we reinforced our understanding of the definitions of aperture stop, entrance pupil, exit pupil by tracing those specific rays through the system. We also had looked at some of the techniques that we as optical engineers or a software like Oslo uses in order to trace a ray through a system. So we are going to continue along these lines, and today we are going to look at what are called ray tracing matrices. Okay, they are also sometimes called transfer matrices. Or ABCD matrix. Okay, so we use this technique, the ray tracing matrix, when we are dealing with systems, optical systems, and let's be a little more specific. We use this when we are dealing with circular symmetric optical systems. Of course, they all will have the optical axis, which is the center of symmetry. We are considering systems that could have a number of elements in them, so they contain refractive as well as reflective surfaces. And we are going to use this technique to trace what we call meridional rays. Okay. Now, what do I mean by that? Let's say I have, this is my optical system, or rather this is the optical axis. I am talking about rays that lie in this plane. Okay. What is this plane? The ray is generally traveling in the z direction, or in other words, the z axis is the optical axis, and the ray is, I have shown it go up and down. Clearly it's met an interface and therefore it has bent, but all of this is happening in this plane. Let's say in this case I call this the YZ plane. So I am talking about rays traveling in a plane. This plane contains the optical axis, but I am not talking about rays that get pushed out of this plane. Okay. So these are meridional rays. They lie in the YZ plane, and this also happens to contain the optical axis. You can have rays called skew rays, and as the name suggests, they don't travel in a plane, but they travel in a skewed fashion. So you could imagine if you had a hollow cylinder and you sent light into that hollow cylinder and it bounced around, and maybe it went to this side and then it went up here and then it went down here. It's no longer in one plane. You couldn't put one plane and capture the entire path of this ray as it traveled through this hollow cylinder, right? You can't use this technique to trace those kind of rays. Of course, in an optical system you may have rays that are traveling, depending on your optical system, you may have skew rays in it, but this technique would not be used in that case. Okay. So we are dealing with meridional rays that lie in one plane, the plane containing the optical axis. Is there only one plane containing the optical axis? There are infinite number of planes, right? So we are taking one such plane and looking at how the rays travel in that plane. Of course, I can apply this technique to each plane. Then I will trace rays in that particular plane, and those are meridional rays too. In this case, I am just defining the YZ plane as my plane of interest. Okay. Okay. Now, the rays, so I have drawn it, this particular image with these rays bouncing, and basically that means there is some interface at these points. But the point to note is that at any instant I can specify this ray with just two parameters. Okay. What are those two parameters? What are the angle, the slope with respect to the optical axis? So, when you say angle, you have to be very clear. In an optical system, it is always the angle with respect to the optical axis. I might, when doing my calculations, take into account angles with respect to normal, but even there finally I reduce that to angle with respect to optical axis. Okay. So, it is the angle with respect to the optical axis. So, in this case, for example, here this would be the angle with respect to the optical axis. At this point, if I were to specify this ray at this point, this is its angle with respect to the optical axis, this is its height with respect to the optical axis. So, if I am looking at this point, right, this is the angle with respect to the optical axis, and this is the height with respect to the optical axis. So, the two parameters completely describe the ray theta and y, and this theta is with respect to the optical axis of the system. Okay. So, let me redraw this diagram. So, this is Z, the optical axis, this is Y, and let us say I am interested at two different points on the optical axis. So, I have a ray that is coming in here, it has height y1, its angle is theta 1, and at some other distance z, this ray is now travelling, and it has now, okay, assume that is a straight line. Okay. So, over here it continues, and at this interface maybe something happens. So, this is theta 2 and this is y2, okay, and this is at z1. So, I know the information of the ray at z1, it is theta 1 y1, and then it travels through some optical element, okay. And I mean even air is an optical element, because just travelling through free space changes y. It does not change the angle the beam is travelling at, the ray is travelling at, but it does change the height. So, I will consider travelling through a homogeneous medium as also affecting the ray. When do we say the ray is affected? If theta and y are changed, or either one of them is changed, the ray has been affected, and we will consider that as an optical element. You should be familiar with this idea, because even in Oslo, travelling through a medium is a surface in Oslo. To change y or theta, you put an interface and something happens. Okay. Okay. So, our goal in ray tracing is to find out y2, the new height and the new slope, given that you know the old height and the old slope. So, I will say there is some relationship, and I am able to do this because I say the relationship is linear. And similarly, theta 2 will be again functions of the old height and the old angle. I'm now, it should be clear where this matrix formulation is coming from, because I'll say we want to find out y2 and theta 2 in terms of a matrix M and the original parameters. What is this matrix M? M is nothing but this ABCD matrix, or it is called the ray tracing matrix. Now again, the convention that I am using here is that y2 is in the first row and theta 2 is in the lower row. Different books, different people use different conventions. They may reverse this, they may put y2 is a theta 1 plus b y1. So you need to know what is the convention before you blindly take an ABCD matrix and use it somewhere, right. I would say stick to this convention in this course, but if you are looking or reading up something somewhere else, don't just blindly look at what's been given to you. Check the convention they are using, because it could be some variation of this. Okay. So how do we use this? The easiest way is to start looking at ray transfer matrices for different optical operations. Okay. So let's start with the simplest optical operation, and that is traveling through free space. So matrices for optical operations, and the first one we are going to do is free space. So for free space, I can just use the figure that I have directly above. When if between Z1 and Z2 is nothing but free space, what do I expect the change to be in y2 and theta 2? Now let's say the distance between these two planes is d. What do I expect the difference to be? What could I say the new y2 will be? It's nothing but y1 plus d theta, or let's be explicit, use the terms we have used. So it's d theta 1. The new height is nothing but the old height plus the change in height that has come because of this extra travel. On the other hand, what has happened to the angle? This is free space. The angle does not change at all. The ray continues to travel along the direction it was traveling in. There is nothing to cause a change in direction. So I know that theta 2 is going to be equal to theta 1. If I write out my matrix now, my ray tracing matrix now for free space, A is 1, B is the distance travelled, C is 0, and D is 1, capital D is 1. So this is the ray transfer matrix for a ray that has travelled through a thickness D of free space, right? Okay, let's do another one. Let's say we do refraction, and we'll first take up refraction at a planar interface, a planar boundary. Okay. Always considering paraxial rays, so if I have a ray that is incident with some angle theta 1, it is getting refracted at angle theta 2, it's n1 before this, it's n2 before this, and its height is y. let's say it's y1 to start with. How does the height of this ray change as it crosses the interface? There's no height change, right? At the interface, we are only looking at what happens at the interface. Of course, if I look at the ray at some other distance d, there is a height change. But now the matrix that we are trying to arrive at is not to do with the travel through this distance, it's only what happens at this interface. At this interface, the height before the interface was y1 and the height after is y2, but they are equal, because clearly at the interface it's not that the incident ray does this and the exiting ray does this. This is not what happens, right? Obviously this is not what happens. So y2 is directly equal to y1 here. But unlike the previous case, the angle is going to change because you have refraction at the surface. We are talking about paraxial rays, so I can write my Snell's law as n1 theta 1 is equal to n2 theta 2. In other words, theta 2 is n1 by n2 theta 1. My ray transfer matrix in this case is 1 0 0 n1 by n2. Let's do a third one, refraction at a spherical surface. Now, we actually did this derivation in part last time, arriving at this equation, but let me just draw it again anyway. That's your optical axis, that's your spherical curved surface, right? If we were to continue, you would get a circle. The center of that circle is over here. So if I draw a line out, this is going to be normal to the interface because it's coming from the center of that circle. And then I have an incident ray, I have a refracted ray. I can draw my optical axis here again. What are all the angles that we have now? Well, we have this angle theta, which is the same as this angle theta. With respect to the optical axis, I have theta 1 here and theta 2 here. But I want to use Snell's law at this surface. So this angle is the incident angle and this angle is the reflected angle, right? It's surface with refractive index n1 here and n2 here, and again what's the height of the ray? Well, it is y1 before the interface and it is y2 after the interface, because again we are finding the ray transfer matrix for refraction at the curved surface, not after any propagation. So at that point when the ray hits the interface, at that point of hitting the interface, the angle changes after the interface, but the height does not change. So we are again going to write this condition because this is true at this surface. We need now from this figure to figure out an expression for theta 2 in terms of theta 1, right? So let me do that here. We start with Snell's law. So that is n1 theta I is equal to n2 theta r, which is nothing but theta plus theta 1 theta plus theta 2 and n2 theta 2 is going to be n1 theta plus n1 theta 1 minus n2 theta. So I can write this, and in fact I am interested in theta 2. Now I can of course just transpose and write this equation over here saying I have theta 2 in terms of theta 1, but I am going to change one thing just to put it into parameters which are more measurable. So, I will not use theta directly, but I will say theta is y by r, because remember this is theta, and since y1 is equal to y2, I can also go ahead and say this is y1 by r. Yes. So, now I will say I have theta 2 in terms of theta 1. What is the equation I have? I have minus n2 minus n1 by n2 y1 by r plus n1 by n2 theta 1. And again I can write out the ABCD matrix for this. In the first case it is 1, the coefficient here is 1, right, and below that the coefficient of y1 for theta 2 will be minus n2 minus n1 by n2 r. There is no theta 1 term in the height, so there is a 0 there, but theta 1 does appear in the theta 2 expression. So, I have n1 by n2 here. So, this is the ABCD matrix for refraction at an interface. Okay, so fairly straightforward, I think, right? Any doubts, any questions? No. Okay. So, instead of me working out the next one, I think it makes sense if you work out the next one, and I want you to work out now for a lens. So, what is the ABCD matrix for a lens? And let us make it really simple. So, I am going to say a thin lens. So, we are talking about paraxial rays hitting a thin lens. Okay. So, just to allow you to recollect that the way I would draw a thin lens under paraxial optics regime is I would just draw it as a straight line like this, right. Okay. But that does not mean you will apply Snell's law here. Right. What are you going to do to calculate the lens? What do you think the power of this matrix method is? I've done 3 cases, and we found one matrix, and then we found another matrix, and then we found another matrix. How do I trace a ray finally? How do I use these different matrices to trace a ray through a system? You are going to cascade the matrices, right? So, if I have 10 optical operations, and even traveling through free space or traveling through a homogeneous medium will be considered an operation, I will have 10 different ABCD matrices, and I will cascade them. How will I cascade them? Well, let us say I had the first operation here, the next here, the next here, the next here. This is M1, this traveling through this is M2, this is M3, traveling through this is M4, this is M5, this is M6, this is M7. In order, and I know the height of the ray and the angle of the ray before the system, and I want to find out those parameters after the system. A simple cascade operation is going to give me this, but I have to be very careful when I do the cascading, because the first optical operation seen by the ray is that given by M1. So, when I write it out mathematically, I am going to write out M7, M6, M5, M4. Right? So now I am asking you to find out the ABCD matrix for a lens, a thin lens. You can use a cascade operation to do that. What are you going to cascade? What matrices will you cascade? You don't have much choice. I haven't given you 7 or 10 matrices yet. We've done just 3. Right? So clearly some combination of those 3 has to be the answer. So out of those 3, which ones will you use in order to arrive at the thin lens formula? Sorry? Exactly, you will use the last one we did, refraction at a spherical surface, because a thin lens, a ray is going to encounter first this surface, radius of curvature r1, and then it's going to encounter this surface of radius of curvature r2. It has refractive index n1 before it, it has refractive index n2 before it, and let's say it has refractive index n1 again after it. Okay. Now, I've drawn it like this, and you might say, but there's a distance in between. Well, that could be another exercise to say, take into account the fact there is some thickness to the lens. But I am making it simpler for you and saying, let's assume the distance d is 0. Where does that help us? It means that I know y1 and y2, I will consider them the same. The ray height after the lens will be the ray height before the lens, because it hasn't traveled through any thickness of the lens. Okay. So then it's a simple cascade of these 2. It's actually the same matrix, but I have to change the parameters to suit these conditions. So can you do that and arrive at the answer for me? Okay. So what are the, so the A term is 1 into 1 plus 0 into this, it's nothing but unity. The next parameter B is 1 into 0 and 0 into this, so it is 0. So what is of interest now is the C parameter, right, and that ends up being the sum of this term here, this term, plus the product of this and this, right. So, if I write that out, I will get minus n1 minus n2 by n1 r2 plus, and there is a negative sign there. So, it is going to be n2 minus n1, n2 and n2 cancel out. So, I have n1 r1 over here. Let me erase this. And then finally, the d parameter is the product of these 2 ratio of refractive indices, and you're left with 1. Okay. That 1 comes about because you had refractive index n1 on either side of the surfaces. If I had n1, n2, n3, I wouldn't have got that 1 over there, right. Okay. Now, if I look at this term here that I have not simplified, the term in red, I can simplify this term and it should look familiar after you simplify it. So, I can take this term and I could write it as minus n2 minus n1 divided by n1, that is common to both the terms, and I have 1 by r1 minus 1 by r2. It is not surprising what this represents. It is nothing but 1 over the focal length of this lens, and that was what you set out to prove. Right. So, now you know that if your lens is not a thin lens, it is very easy for you now to arrive at that equation. Do you remember how we arrived at this equation the first time round? I drew out that whole figure, we traced a ray, then we said this is where the object is. If the object is here, this is where we assume the image is. Then we use this as the image point, this image point as the object for the next surface, and then we calculated and said using this image point as object for the second surface, here is where the second image and final image is. I mean, just those 2 surfaces, and it took quite a bit of time and effort, and it's easy to make a mistake somewhere. And you can see now with this matrix method is so much easier. In fact, why two surfaces? I could add thickness, so I forget thin lens, we can make it a thick lens. Plus, I could say then after the first thick lens, it travels a certain distance d, then I just insert that matrix, and then it encounters another lens, and I can either just write it in terms of, so I can calculate what happens when I encounter a lens using this whole formulation that we just did, or I could say the ABCD matrix for a lens, for a thin lens, is nothing but 1 0 minus 1 by f, sorry, 1. This is the ABCD formulation for a thin lens. So you should be able to see now how much easier it is, how much less error prone it is to just use these matrices and trace any meridional ray through the system. And should be clear why it has to be meridional, why it has to lie in the plane, because the way we are defining those angles, it will not work if the angle is now moving into another plane, right. I can use this two-dimensional definition and trace a ray very easily. Okay. Okay. So we've looked at 4 different, or was that, actually this was the 5th one, right? Well, we'll call this 4B because both are thin lens. So one we have calculated and written it out in terms of N1, N2, R1, R2, but that is the same as writing it in terms of the focal length of the lens. Okay.